Today, our topic is tunnel diode or Isaki diode. So, before going to tunnel diode, I would like to explain the basics of semiconductor devices. So, semiconductor devices are used to manufacturing these electronics components. So, semiconductor devices are two types. One is intrinsic semiconductors and other is extrinsic semiconductor. So intrinsic semiconductors is nothing but pure semiconductors, whereas extrinsic semiconductors is nothing but impure semiconductor. So when the impurities are added to pure semiconductors, then we call it as impure semiconductor or extrinsic semiconductors. So extrinsic semiconductors are two types. One is p-type material and other one is n-type material. Okay, based on the doping levels, that material can be used in different purpose. So adding impurity to the material, semiconductors material or intrinsic material, we call it as doping. Okay, in our real-time example, we are adding. So we have milk, we are adding buttermilk to the milk. What happened? We have some advantages. So it prepared curd. After making curd, we will get cheese. After that, we will get ghee. From ghee, we can use many preparations like sweets. So many advantages. We are adding a suitable impurity to the milk. So that suitable impurity, we call it as buttermilk. We are adding suitable impurities. We have more advantages. So simply we are adding buttermilk to the milk. That is, buttermilk is the suitable impurity to the milk. We have many advantages. For example, in reverse way, so we have milk, we are adding lemon to the milk. So actually lemon is not a suitable impurity. So we are adding to the lemon to the milk. What happened? So paneer is created. So by using paneer, so only one advantage. While adding lemon to the milk, paneer will be created. Whereas while adding buttermilk to the milk, curd, then cheese, then ghee, then see many advantages. That's why in like semiconductor also we have to add suitable impurity to the material, we will get more advantages. So in this scenario, we are adding suitable impurities to the normal PN junction, we can get more advantages. So we are talking now diode applications. So in diode applications, heavily doped diode are many, Zener diode, varactor diode, tunnel diode. So these diodes are same, but concentration or doping levels are different. Based on doping levels, these diodes characteristics are differ. Today we will see tunnel diode in detail. Okay. So tunnel diode is also called as Isaki diode because the name Leo Isaki is found this diode. So it was introduced by Leo Isaki in 1958. So as we know, tunnel diode is a heavily doped PN junction diode. It is a normal PN junction diode, but impurity concentration or doping levels are more compared to the ordinary diode. If doping levels are more means this diode exhibits different characteristics, different conductivity characteristics. Okay. So impurity concentration is 1 part 1 path in 10 cube as compared to 1 path in 10 power 8 in PN junction diode, because that means it is a heavily doped diode. That means it is a heavily doped. 1 path in 10 cube means it is a heavily doped. Whereas normal diode 1 path in 10 cube. 1 path in 10 cube means it is a less compared to 1 path in 10 cube. Okay. Because of heavily doped, the bandwidth, not bandwidth, the width of the depletion layer is very small. The width of the depletion layer is very small. Why it is very small? We know the function. So depletion layer. So depletion layer or depletion region or depletion barrier. So depletion dB, I can call it as depletion barrier, is equal to 1 by impurity square. 1 by impurity square. 1 by impurity square. That means while adding more impurities, depletion barrier width is decreases. While adding more impurities or doping levels are more means barrier width is decreases. That means barrier width is inversely proportional to the impurity concentration. Okay. So we know that tunnel diode is a heavily doped. Heavily doped means impurity concentration are more. So impurity concentration are more means barrier width is very less. It is a very thin. Okay. So these tunnel diode can be manufactured by using germanium or gallium arsenic materials. Okay. So why we call it as tunnel means, so in working principle of tunnel diode, there is a tunneling mechanism or tunneling phenomena is there. I will explain within a short period. So that's why we call it as tunnel diode. So the symbol of tunnel diode is like this. The symbol of tunnel diode is like this. See, it is a two terminal, anode and cathode. So we know the tunnel symbol. So this is the tunnel symbol. So this is the tunnel symbol, already we know. So this is only one line. This is a tunnel symbol. So anode means positive, cathode means negative. So this is the diode symbol. Okay. So this tunnel diode can be, tunnel diode characteristics can be expressed in two ways. One is by using voltage and current characteristics, and other method is energy band diagram. So we will see one by one. First we will see the voltage current characteristics of tunnel diode. So this is voltage current characteristics. So by seeing this figure, we can observe that, so this tunnel diode is operated in a forward bias. By seeing this figure, we can simply say that tunnel diode is operated in a forward bias, because this region is a forward bias, because VF is the forward voltage and IF is the, so VF is the forward voltage and IF is the forward current. That means these characteristics are in forward bias. So voltage is more than 0. So forward bias. Okay. So by seeing this graph, we'll observe that whenever 0 voltage, so VF is equal to 0. So this point, VF is equal to 0. So current IF is equal to 0. Okay. Whenever forward voltage VF is increased, approximately I call it as 0.1. VF is equal to 0.1. Whenever applied voltage or forward voltage is 0.1, current is sharply increases. Whenever applied voltage VF is equal to 0.1, current is sharply increases up to a point A. So corresponding current, we call it as peak current, and corresponding voltage, we call it as peak voltage. Okay. Again, we are increasing. So what happened? Why this current is suddenly increases up to this point? Because we know that, so tunnel diode is a heavily doped diode. So this is the tunnel diode is a heavily doped diode. So this is the P, this is the N. Okay. So heavily doped means barrier width is very less. So this line, vertical line is the barrier. It is very thin. Approximately it is like a hair width, means it is less than 5 micron. Sometimes we call it, it is invisible, that much sharp bandwidth is. So whenever 0.1 voltage, so applied voltage is 0.1 voltage. Whenever 0.1 voltage is applied, it is a diode. It is a diode. Whenever 0.1 voltage is applied, what happened? Because barrier width is very less, it is compared to hair width. So electrons are easily move from N to P. It is moved from N to P. We can say that these electrons are penetrated because this width is very less. So these electrons are penetrated to the barrier or depletion. So that's why these electrons penetrating this phenomena, we call it as tunneling. We are applying very less voltage, so barrier width is very less. So because of barrier width very less, electrons are easily move or cross these junctions. Instead of crossing this junction, these electrons are penetrated through the junction because it is very thin, like hair width. So penetrating. So this phenomena we call it as tunneling. So in tunneling situations, current is high, very high, up to this point. Up to this point. Again, we are increasing 0.1 to some 0.2. What happened? Current is decreases. Current is decreases up to a point B. This point we call it as valley current or corresponding voltage. We call it as valley voltage. Corresponding current we call it as valley current. Corresponding voltage we call it as valley voltage. So between valley voltage or peak voltage to valley voltage, this region we call it as negative resistance region. This region we call it as negative resistance region. Okay, we are increasing the forward voltage, but current is decreases. So this region from peak voltage to valley voltage, this region we call it as negative resistance region. Because of negative resistance region, this tunnel diode can be used as a relaxation oscillator. Okay, again we are from valley point, again we are increasing the forward voltage. So current is increases like normal PN junction diode. So this is happened because of injection of electrons. This is happened because of injection of electrons. So this is the characteristics of tunnel diode. I will repeat so you can concentrate. So whenever 0.1 volt is applied, current is suddenly increases because barrier width is very less. Instead of cross the barrier, electrons are tunneling through the barrier. So at that time, current is very high. That current we call it as peak current. Again, we are increasing the forward voltage. Current is decreases up to a point B. This point we call it as valley point, or corresponding current we call it as valley current. Corresponding voltage we call it as valley voltage. Again, we are increasing the VF from 0.1 to 0.2 like that. So current is increases like ordinary diode because of injection of electrons. So this is one method for describing the characteristics. So another method is energy band diagram. So we know that the basic energy band diagram, we have valency band VB and conduction band. So this is a P type and this one is a N type. So valency band, conduction band, in between energy gap, or we also called as forbidden energy gap. So we know that tunnel diode is a heavily doped diode. If heavily doped diode means what are the majority charge carriers in P type? So generally majority charge carriers are P type means holes. Majority charge carriers in N type means electrons. So this black dots, we call it as electrons. This electrons, this we call it as holes. So in both type electrons and holes are there because it is a heavily doped material. So heavily doped means instead of less number of holes in P type, heavily doped means more number of holes are exist in the valency band. Similarly, it is a N type is a heavily doped. Generally in N type majority charge carriers are electrons, but it is a heavily doped means more number of electrons are there in conduction band. Okay. So this is the P type, this one is the N type. So these two we call it as energy band diagram of two types of silicon. So it is a P type material, it is a N type material, but it is a silicon material. Okay. So this is the energy band diagram. So whenever this energy band diagram, we are combined together P type and N type. So this is a P type, this is a N type. We are combining together. What happened we will see. So whenever we are combining together at 0 degrees or 0 voltage, what happened? This valency band is misalignment. Whenever P type and N type are combined, this valency band is misaligned. See, this valency band is move above compared to previous one. So this is the valency band. Now, whenever we are connecting both P type and N type, this valency band is move above, upwards. Now there is no equal levels. See, conduction band is there here and valence. So there is no equal levels. So there is no equal levels. It is different. So there is no current conduction. There is no current conduction. Whenever this valency band and conduction band levels are same, then only electrons and holes are exchange. Electrons are move. So this region we call it as, depletion region. Depletion region or barrier potential. Okay, depletion region. This region we call it as depletion region. This region we call it as depletion region. Okay. So there is no equal alignment. So there is no conduction. We are not applying any voltage to this tunnel diode. So this is at 0 voltage. Now we will apply voltage like 0.1 volts, for example. It is a small forward voltage. Whenever small forward voltage is applied, what happened? This conduction band is move above. This conduction band is move above. Now we will see both levels are equal. Both levels are equal. We will see both levels are equal. So valency band and conduction band levels are equal. So we know that tunnel diode is depletion layer is very less, very thin, like hair width. So electrons easily move from this conduction band to valency band. Instead of moving, instead of crossing, it penetrates. It penetrates like this. It penetrates like this. Okay. Because of very thin. It is very thin, like hair width. So at this situation, current is very high. So this mechanism we call it as tunneling. So whenever 0.1 volts is applied, small forward voltage bias means 0.1 volts is applied, there is a tunneling occur because both are valency band and conduction bands. So valency band in P type, conduction band in N type, both are same level. So electrons are easily moved. Instead of moving this junction, so it is penetrating. Penetrating means we call it as tunneling. So in this tunneling situation, current is very high up to peak. Current is increases very sharply whenever we are applying small forward voltage like 0.1 volts. Now I am applying 0.1 greater than 0.1. So bias is increased from 0.1 to 0.1 to or 0.1 to some other voltage like 0.2 like that. So whenever bias voltage is increased, this conduction band is move upward again. See here, levels are equal. Levels are equal for a small forward bias. If bias is increased, this conduction band is again move forward. Now this is same position. This conduction band is move forward. So there is no equal level. There is no equal level. So there is no movement of electrons. So there is no current. So there is no current means from peak point to, so current is increases peak. So in this situation, so these levels, conduction band and valency bands are different means there is no current conduction. So current is decreases up to some level. Again we are increasing the forward bias. What happened? Current is increases like normal diode. So this is the peak current. This is the valley current. So this is the in between we get negative resistance region. Okay. So this is the characteristics of tunnel diode. So whenever forward voltage more than 0.1, tunneling will be stopped. Whenever bias is increased 0.1 to some other voltage more than 0.1, tunneling will be stopped because this conduction band and valency bands are not in same level. Here this valency band and conduction bands are same level. If same level only, current conduction is possible because of it is a thin layer. Instead of crossing the junction, these electrons are penetrated. This phenomena we call it as tunneling. Here full tunneling occurs. That's why current is increases more up to peak point. Here tunneling is stopped, current is decreases. So this is the characteristics of tunneling diode by using energy band diagram. Okay. So this is the equivalent circuit of tunnel diode. So you can observe, so this is the junction capacitance. So this is the negative resistance. This one is lead inductance. This one is lead resistance. So this is the equivalent circuit of tunnel diode. So you may doubt where it is junction capacitance is exist, you may doubt. So in junction, always positive ions and negative ions are there in junction because of, so this is a positive, this is a negative, this is a positive, this is a negative means, so parallel plate capacitance is exist. So there is a capacitance exists, that capacitance we call it as CJ. CJ means junction capacitance. Okay, junction capacitance. This is the reverse resistance or negative resistance, lead inductance and lead resistance. These are the leads. Okay. So what are the applications? So tunnel diode as ultra high speed switching with a switching speed of order of nanoseconds to picoseconds. Why it is very high speed, ultra high speed? Because junction width is very less. Junction width is very less means electrons are penetrating means, so very high speed. So tunnel diode is used as a ultra high speed switch. the speed order of nanoseconds to picoseconds. So as a microwave oscillator, because of negative resistance characteristics, it can be used as a microwave oscillator. Okay, and also relaxation oscillator. So what do you mean by oscillator? It generates a sinusoidal signal oscillators. Okay, it is an amplifier also. It can be used as, our applications are amplifier. A logic memory storage device can be used as a logic memory storage device. So what are the advantages? So advantages are very low noise and easy of operation and high speed, ultra high speed. These are the advantages. It is low power. We require low power because voltage is very small. We know the power formula. Power is equal to I square into R. Some other formula, P is equal to V square by R. So if voltage is very less, means power is very less, low power. So this is the power formulas. So in the form of current, in the form of voltage, power formula. Here, less power means voltage is very less, approximately 0.1 voltage, we will get more current. So more current means, less voltage means power is very less. Next, disadvantages. So voltage range over which it can be operated 1 volt or very less. So this is one disadvantages, but many of electronics appliances will require more than 5 volts. So it is less than 1 volt means this is one disadvantage. So other disadvantage is there is no isolation between input and output circuit. There is no isolation between input and output circuit. Okay. So this is the tunnel diode. So I will summarize this tunnel diode. So tunnel diode, we also called as Isaki diode. It is introduced in 1958. Tunnel diode is a heavily doped PN junction diode. So it is generally made up of germanium and gallium arsenide. So because of tunneling phenomena, this diode can be called as tunnel diode. So the circuit symbol is like this. Circuit symbol is like this, tunnel diode. So it is the tunnel symbol, one line. Whereas GNR diode symbol is like this. So Z symbol. Here, this is the symbol. Okay, tunnel diode. Next, so tunnel diode characteristics are explained in two methods. One is VI characteristics, other one is energy band theory. So VI characteristics means when forward voltage is increases, whenever forward voltage is very less, current is increasing very sharply up to a point A. That point we call it as peak point. Again, we are increasing the forward voltage, current is decreases up to a point B. That point we call it as valley current. Corresponding voltage we call it as valley voltage. Again, we are increasing the forward voltage. Current is increases like normal diode. So this is the characteristics of tunnel diode. Between A to B or peak voltage to valley voltage, tunnel diode exhibits negative resistance characteristics. Negative resistance characteristics. So you can observe tunnel diode is operated in a forward bias. See, this is in this quadrant. It is a forward bias. If it is here means it is a reverse bias. So now it is a forward bias. Okay. And also energy band diagram we can explain. Semiconductor materials are, this is the p-type material, this is the n-type material. Generally p-type material, the majority charge carriers are holes and minority charge carriers are electrons. Minority means less, see, less number of electrons, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Here holes are 16 holes are there. So majority, okay. In p-type, n-type, majority charge carriers are electrons, minority charge carriers are hole. Okay, it is a heavily doped material, means more number of holes in p type, more number of electrons in n type in conduction band, holes in the valency band in p type. So whenever both materials, p type and n materials, are combined without giving any voltage, there is a misalignment. Misalignment means this valency band is move upwards, slightly move upwards. There is no equality between conduction band and valency band at zero voltage. Whenever we are giving small voltage like 0.1, so here this, see, valency band holes are in above, here conduction band electrons are below. Whenever small voltage is given, this conduction band is moved to here, up to here, for a 0.1 volt. Now conduction band and valency band, this is the conduction band, valency band, both are same levels. If same levels, current conduction is exist. So because of heavily doped means less barrier width, so electrons are penetrating. This penetrating mechanism we call it as tunneling mechanism. So in small voltage, full tunneling occurs. Because of full tunneling, more current will occur up to a peak point. So peak point current we call it as peak current. Corresponding voltage we call it as peak voltage. Okay. Again we are increasing the small forward volt bias to some bias is increased from 0.1 to some 0.2. So again increasing means this conduction band is move upward. Now valency band in p type, conduction band in n type, both levels are differ. There is no tunneling. If levels are same, then only this electron movement will be there. If levels are different, means there is no electron movement, so tunneling will stop. Tunneling will stop means current is decreases to up to a point b. Then we are increasing the current, then again current is increases due to injection of electrons. This is the operation of tunneling diode. So tunneling diode can be used in many applications. So many applications. One is high speed switch, microwave oscillator, relaxation circuit, amplifier, logic memory storage device. Noise. Advantages are noise, easy of operation, high speed, low power. And disadvantages, only we are using less than 1 volt only it can be used. So there is no isolation between input and output circuit. So this is the tunnel diode. Okay.